Okay, well, gone 5 o'clock, so let's make a start. Good morning to those of you on the West Coast. Good evening to those of you joining us from the East Coast. And good evening to anyone joining us from Europe or stations further east. I'm glad you managed to cope with the fact that in the UK, the clocks went back 1 hour last weekend, and most of you seem to have taken that into account and arrived on time. Thank you for joining this, the 9th of our regular series of short courses on pumping topics. This one will last about 30 minutes, allowing us plenty of time for a Q&A session after the presentation. As in previous sessions, we're trying to maintain educational content rather than product placement. So what I'm telling you today is as applicable to Ruhrpumpen as it would be to any other pump supplier. We are into session 9 now, and I expect most of you will have attended one or more of the previous sessions. So I will fast forward past the usual 5 or 6 slides, reminding you of who we are and what we do, and get right on to the topic at hand. The slides will be in the PDF copy you'll receive, so you can peruse them at your leisure later on. So let me share my screen again and get the presentation going. So fast forwarding past these until we get to the crux of the matter. And this is what we're looking at today. We're looking at pump instrumentation with a particular emphasis on vibration monitoring and with a section helping you to understand what the readings you obtain tell you about your pump installation. As usual, we'll be holding a Q&A session at the end. Now, it won't be fully interactive. We'll do the best we can. The last count, there were 180 people registered for this session alone, and we've averaged about 200 attendees for all of the previous sessions. So difficult with that many to do a fully interactive one, and so we'll just do the best we can. Please use the Q&A button at the bottom of your screen to ask any questions or make any comments. I'll address those that I can live at the end of the session, and the rest we'll address by email in the coming days. We are recording this session and we'll make it available to all attendees as a YouTube link, as well as by emailing you a PDF version of the slideshow and a summary of the questions and answers from both the sessions that we've had today, the morning session and this afternoon session. So, why is your pump vibrating and is it serious? This is what we're going to look at today. There are 2 general physical causes of vibration: mechanical causes, balancing, misalignment, bearings, and hydraulic causes, liquid turbulence, cavitation, and suction and discharge recirculation. When we're measuring vibration, we have 3 different vibration measurement devices. Velometers, the most common, which measure the velocity of the vibration. So units of inches per second or millimeters per second. Then you have accelerometers, which measure the rate of change of velocity over time. So the units are inches per second squared or millimeters per second squared. The third one is displacement vibration proximity probes. These are used in pumps which have journal, sleeve, radial bearings, and tilting pad thrust bearings. These probes measure the displacement, the slight movement of a rotating component, the shaft. And so the measurement is in mils, thousandths of an inch, or microns, a peak-to-peak reading. Many vibration units will measure vibration either in RMS or in peak-to-peak. Most commonly, they're given in RMS values, with peak-to-peak values used for detailed analysis. So RMS, root, mean, square, which means you take all your peak-to-peak values, you square them, you take the average, and then square root that total. So for example, if you've got 3 peaks here, you square them, add them together, divide by the total number, and then square root it. So the RMS of these 3 peaks is 0.118. Vibration is measured in 3 planes: horizontally, vertically, and axially. And API 610 shows us where we have to measure them. Horizontally, vertically, and axially, there will be dimples on the case to show consistently where you will be measuring. And it can be done 2 ways. It can either be with a handheld meter, which is when you need the dimples, or you could have a permanently installed accelerometer or velometer. This shows simplistically how an accelerometer works. Vibrations on the pump bearing housing cause the mass inside the accelerometer to squeeze the piezoelectronic, it's a mouthful, piezoelectronic material, which produces an electrical charge proportional to the force exerted, so proportional to the vibration. That's an accelerometer. A velometer, generally they are the same as accelerometers, but they contain integration circuitry, which converts acceleration to velocity. And API 610 specifies vibration limits in velocity units. Here is table 8 from API 610, and it shows the vibration limits for anti-friction ball bearings. So for flow rates within the pump's preferred operating region, remember the preferred operating region is from 70% to 120% of the best efficiency point flow, 70 to 120%. So within that range, the velocity, vibration velocity must be less than 3 millimeters per second or 0.12 inches per second, root mean square. Outside of that preferred operating region, so fundamentally from minimum continuous flow to 70% of BEP flow, you can have a 30% uplift on that. So 3.9 millimeters per second instead of 3, or 0.16 inches per second. When you have sleeve bearings, then you use displacement proximity probes that measure the gap between the shaft and the bearing sleeve. This is a little wordy, but if you look at it carefully, the 2 radial probes here and here, they're powered by a proximeter, which provides an alternating high frequency voltage to the coils within the proximity probes. This causes an alternating electromagnetic field at the probe tip, which is to induce alternating eddy currents in the shaft. These eddy currents generate a magnetic field emanating from the shaft, which opposes the field from the probe. So as the gap between the probe and the shaft varies, if you've got a bent shaft, for example, the magnetic field interaction would change as well. The probe electronics measure this field change and generates an output voltage proportional to the change in the gap. So the probes are accurately measuring the radial movement of the shaft in mils or microns. If you have sleeve radial bearings and ball thrust bearings, then you'll have proximity probes for the sleeve bearings, and for the ball thrust bearings, you'll have accelerometers. But if you have sleeve radial bearings and a tilting pad type thrust bearing, then you'll have another proximeter reading in the Z direction on the non-drive end of the shaft. So here, measuring in that direction instead of that direction. Here are the vibration limits for sleeve and tilting pad bearings. And here on the left is the key. You see we've got the amplitude, and it's this function of the speed of the pump. And that's going to give you the answer in peak to peak micrometers, or here in mils. Now, as well as the X, Y, Z proximeters, you'll also have a key phaser proximeter aimed at a keyway. This will identify where the shaft displacement that is measured by the X and Y probes, it will identify where it's occurring, referenced to this keyway. So for example, it identifies that a shaft might be bent at 20 degrees away clockwise direction from the keyway, for example. It also can act as a tachometer to accurately read the speed. Moving on to troubleshooting. So you're getting an elevated vibration reading. The first thing to consider is this high vibration reading associated with a sudden power increase or decrease? So first, if it's associated with a sudden power increase, you've got high vibration and a power increase, there are 7 things to look for. Firstly, piping loads. If the piping loads are excessive, you could be distorting the case and causing wear ring contact. So if the impeller wearing is touching the case wearing, you're going to get rub, damage, and higher power, as well as vibration. Secondly, extreme wearing wear. Your clearances will open up, they might be double, and this allows greater recirculation, hence reducing the efficiency and increasing power again. Third thing to look at your system resistance curve. Maybe there's a bypass valve that's a fixed open. So the pump discharge flow has increased. If you're increasing your flow, your power will increase. Check the anti-friction bearings and check the oil level, oil quality, and oil grade is correct. And I would say particularly oil level. Too high an oil level is worse than too low an oil level. I've seen pumps overheat and vibrate badly just because they had too much oil in them. If your bearings are oil mist lubricated, then verify that the oil mist system is working correctly. Possibly there could be mechanical seal problems. They might not be leaking yet, but you've got potential problems. So check your seal piping system and the flush is working correctly. Check if you've got a plan 62, a quench on the outboard seal, particularly if you're handling something that crystallizes like sodium hydroxide. When sodium hydroxide migrates through the mechanical seal, if it meets the air, it will crystallize and could tear the faces. Similarly, a hot oil pump. Hot oil coming into contact with the air can make coke, and that again can can damage your seal faces. So again, you'll get a power increase and a vibration. And finally, bearing oil temperature. If your oil's too hot, if the viscosity gets down to 11 centistokes or lower, the bearings start skidding. So those are the 7 things to look at immediately if you see a vibration and a power increase. Now, power decrease. Cavitation. Okay, if you've got cavitation, you're going to get lower pump flow, lower pump head, and hence the power will reduce. You're obviously going to have vibration. You'll also have that telltale sound that sounds as if somebody's put a handful of gravel in the suction of the pump. Perhaps you have an inline suction filter not being monitored. Check for blockage. If it's blocked, you'll be restricting the flow. It could be causing cavitation, but either way, you've got low flow, low head, lower power. Again, look at your system resistance curve. Maybe if your system curve has gone up due to some sort of upset, it might mean that the flow is lower. So if your flow is lower, your power will decrease. And the last one to look at, maybe your minimum flow bypass line has an ARC valve that is stuck shut, in which case the pump will be operating below its minimum continuous flow, a lot of vibration, lower power because the flow is so low. Okay, so those are the obvious. Those are the quick and easy things to check when you have a vibration problem. And once you've eliminated the obvious, we can look at vibrations in more detail. Detailed spectral analysis is very much a specialist field. I'm not qualified to lecture on this, and it's certainly well beyond the remit of a 30-minute short course. But this is the kind of analysis that a vibration specialist can offer you. But what I will do in the next 8 slides, is vibration analysis for dummies. It's a crib sheet to give you a clue as to what might be happening to your pump at various frequencies. So looking at the first of the 8 slides, vibration frequencies, 0 to 40% of running speed. 10% of the time, seal faces are dry. 20% of the time, wear rings are rubbing. 90% of the time, you've got thrust bearing damage. And 40% of the time, casing mounting bolts are loose. Well, that's a really easy one to check. So that was the first thing I would check straight away if I had vibration frequency, high vibration in this frequency, 0 to 40% of running speed. And after that, then take the pump out of service so that you can look at the bearings. Similar story here. This is the second of 8 slides. Now, I'm not going to go through every slide in detail. You get the picture. This course would go on for an hour instead of 30 minutes. Same again at between 50 and 100% of running speed. This one is interesting. These are peaks at 100% running speed. Note that 90% of the time, it's a rotor, unbalance, or a bent shaft. And 40% of the time, it's misalignment. So again, this is the easy thing to check: the pump, motor shaft, and coupling alignment. And if you've still got a vibration after that, take the pump out and check the rotor. 150% of running speed. And here at 2 times the running speed. Yeah, 50% of the time it's excessive piping forces and moments. So that's the first thing to check. Check your suction and discharge piping connections. And the 50% of the time it's misalignment. So again, inspect your alignment. Vane passing frequency. The frequency that the impeller vanes pass the casing volute lips or cutwaters. And that's 90% of the time it's going to be that. However, that is something that you're going to see. It's a design issue on a new installation. It's not something that you're going to see during ordinary running. It's not a wear problem. So if it's something that you might possibly see from the outset. Very high frequency and with peaks varying frequently, 90% of the time it's cavitation. You're also going to have that distinctive noise. Here are all the steps to take. So that's the crib sheet, vibration analysis for dummies. So what do API say? API 610 references API 670, which defines selection, installation, and best practice rules for accelerometers, proximity probes, RTDs, thermocouples, key phasers, and magnetic speed sensors. I'll pause to let you look at this one. It's an extract from API 670. And all API pump suppliers are going to be compliant with API 670 for these instruments. So we looked at vibration, now temperature. For anti-friction bearings, the RTD will be spring-loaded so that it rests lightly against the outer race of the ball bearing, like this. For tilting pad bearings, the RTD will be embedded in usually 2 of the tilting pads. And in sleeve or journal bearings, again, embedded in the material. Probably that type, with a spring clip to hold it in place. Now a few slides to show how the instrumentation is typically installed on various pump types. Here is an OH1 or OH2 pump, 1 accelerometer, 1 RTD, wired to a J-box. And in this instance, the wiring is run in conduit. Now, many customers prefer to see vibration and temperature signals run separately to separate J-boxes, or certainly for them to be segregated within the J-box, so you don't mix millivolt and milliamp signals. Here's a typical between bearings pump with ball bearings. Again, 2 accelerometers, 1 on each bearing housing, and 2 RTDs, 1 resting on each thrust bearing. Again, run in conduit, and there's somewhere around the back of here will be a J-box. Here we have a bigger pump with hydrodynamic bearings. So we will have XY probes here on the non-drive end, and the same on the drive end where we can't see them. We'll also have a Z proximity probe reading on the end of the shaft at this non-drive end. We'll also have a key phaser, again, on the non-drive end, probably the other side of this lube oil inlet and outlet. Total of 8 RTDs, 4 in the radial bearings and 4 in the thrust bearing in here. This is the thrust pot on a vertical pump, VS1 or VS6. European and Asian motors generally don't take thrust loads, so we have to use a separate thrust pot, which is what I'm showing here. Of course, American motors are designed to take thrust loads, so you don't need this separate thrust pot. Your bearing monitoring would then be in the motor. But if you have a thrust pot, this is what you might well get: an accelerometer on one side and here an RTD. Cable management. Okay, on simple pumps, instruments are frequently close enough to the skid edge that you don't actually need a cable run or J-box. However, these are commonly specified and therefore we commonly supply them. On more complicated pumps, between bearings pumps, obviously the instruments must be cabled to one or more J-boxes. And the cable can be protected either by conduit or cable tray. This will normally depend on where the installation is. If it's going in America, you'll probably have conduit. If it's going in Europe, you'll have cable trays. So here are the 2 types: cable trays and conduit. Here we see quite a big pump and cable trays. All the instrument runs running cable trays. Quite neat. Now here we see a simple Oh2 pump with only one instrument, an RTD. But still, there's a requirement in the spec to cable it to a J-box at skid edge. I would question whether that is really necessary, or is it blind adherence to the specification. To my mind, it's as easy to connect to this RTD here as it would be to connect it here in the J-box. Here's a sizable pump with all the wiring run in conduit. Obviously a North American installation. Now, we don't often supply these, but some customers ask for a local push button station. There's no standard design, so they really need speccing up properly to tell us what you want them to do. Generally, the intent is to have something nearby the remotely controlled pump to give visual contact on the equipment before starting it and to instantly shut it down in an emergency. Machinery monitoring systems, usually installed in the remote control room, takes the signals from accelerometers, proximity probes, RTDs, and speed sensors, and processes them to give analytical reports for trending, scheduling maintenance, and predicting failures. Commonly supplied by Bentley Nevada and Metrics, big names in this one. Now, they can be supplied by the pump vendor, or more commonly, they'll be supplied by the EPC. Sometimes the pump supplier will supply the racks for installation in the cabinets being supplied by the EPC. The chances are that you've got several pumps from several manufacturers all going into the same cabinets. The crucial thing, if you're going to ask the pump vendors to supply an MMS, is to clearly specify what you want. Don't just ask the pump vendor to supply a suitable MMS. You don't know what you'll be getting. So let me show you 3 scenarios. First, the simplest, lowest cost system, which is 1 cabinet, 1 common rack for all the pumps. The intermediate option has 1 cabinet in the control room, but 1 rack for each pump. Now, this is probably the most commonly specified way of doing it. And this would be the most expensive system, where you have 1 cabinet for each pump and 1 rack for each pump. This would usually be required when the pumps are installed in completely different locations or pumping stations with separate control rooms. Now, you also need to tell us whether you want temperature monitoring in the MMS. It's quite common for people only to want the vibration monitoring in the MMS, and the temperature signals get sent to the customer PLC or DCS. But sometimes you'll want them into the MMS. So tell us. Likewise, do you need a touch screen display on your panel? Also called an HMI, which is human machine interface, which is not something scary out of Skynet. It's something you have on a Bentley Nevada system. It might well be that you're feeding directly to the SCADA system, and so you don't need a local display. Local displays are quite expensive. Finally, for today, smart pump monitors. These are being pushed by many pump suppliers. This one is the KSB Guard I'm illustrating here. Flowserve has the LoRaWAN system, Sulzer has Sense. So what do? How do they work? You've got an accelerometer and a temperature sensor here mounted, measuring temperature and vibration on the bearing housing, sending it to a transmitter, which sends it directly to the cloud, where it will be automatically analyzed, and you'll be sent an alarm if they recommend you have to change the bearings or something of that sort. Sometimes they are monitored by experienced machinery engineers at the pump vendor, and they might get in contact with you and talk about your pumps. It's mainly of use for industrial users who don't have resident engineers, rather than refineries or production facilities where you often have well-experienced machinery monitoring engineers. But I would be interested to hear of your experiences of using this type of service. Is it any good? Well, that pretty much concludes the fun for today. I just get to advertise the next of the short courses. This is on non-destructive examination. I'll be looking at MPE, LPE, UTE, RXE, explaining when they're appropriate for use, how and when to use them, and the benefits and limitations of them all. I want you to get an understanding of what you'll be getting when you tick all those boxes on a pump data sheet. 18th of November, that's 2 weeks today. Again, 2 sessions, one for the Eastern Hemisphere and one for the Western Hemisphere. That's you guys. The invitation will be published very soon. Put it in your diary. After that, probably vertical pumps, VS1, VS4, VS6. And after that, I don't know yet. What would you like me to cover? Drop me a line at smith@rawpumpin.com and let me know. So I'm going to leave this meeting open for a little while to allow you to post in the Q&A box, and I'll endeavour to answer those that only need a short answer here and now. Those that need a fuller answer, we'll answer them in the next few days. Anything you think of later, email to info@rawpumpin.com. Our marketing team will send out a link to the YouTube recording that we're doing of this presentation, and they'll also email you a PDF of the presentation, as well as a summary of the questions and answers from both this morning's session and this afternoon's session. If you need a certificate of completion for this short course, again, send a note to info@rawpumpin.com. So let me look and see what we've got in the Q&A. Okay. Anonymous attendee says, can you provide future presentations on running multiple pumps with variable speed control for both pumps in parallel and pumps in series? Oh, yes, I like that. That sounds an interesting one. Yeah, I'll look into that. Yes, it might be a bit difficult to do in a half-hour session is what I'm thinking. But no, I'll have a look at that. Thank you. Hameen Baker says, do you have the vibration notes listed in a spectrum graph, 1 times, 2 times, and typical amplitude shapes? We're getting into much more detail. You need a detailed course on vibration analysis for that. This is a 40,000 foot level one, is just to give you an overview when you're talking to a vibration engineer, so you vaguely understand what he's talking about. Anonymous attendee says, how are you monitoring axial vibration when utilizing fan-cooled bearing housings on OH2 and BB2 pumps? I should have put a slide in showing a fan-cooled bearing. The fan is on the end of the bearing housing, and there is plenty of room to put how are you measuring axial vibration when utilizing a fan-cooled bearing? Yeah, okay. How are you monitoring axial vibration when utilizing a fan-cooled bearing housing? Yes, you're right. The fan gets in the way of the axial probe, and I don't know the immediate answer to that. I will speak to one of our engineers and get the answer for you. Ronald Franco says, are there any new technologies you're aware of for vibration and temperature sensors, wireless options? Well, if you looked at the last slide I did, the smart meters is the way. They are non-contacting largely. They're sitting on top of the bearing housing, and they're not as accurate as proper screwed in measurement items. Keith Jones says, in API 610, what does the term vibration harness include? I'm not familiar. You'd have to give me a paragraph number for me to look at. Sorry, I don't know. Jay Lee says, when do you start applying proximity type sensors over accelerometers? Simply if you are using sleeve type bearings rather than ball bearings. Karthik says, API 670 doesn't provide which sort of machines need monitoring. Example, high energy pumps or small OH2 pumps. No, it doesn't specify. It's really up to you to decide how critical the application is. The more important the pump is, the more instrumentation you're likely to put on it. Most overhung process pumps in general service duty, you don't really need any vibration monitoring at all. But if it's in critical service, you do. It's a value judgment. It's not one that we pump vendors can make. It's really down for you. Karthik says, any company other than Bentley Nevada and Metrics? I'm sure there are. Those are the two main ones that we get involved with. Those are all the Q&A in that section. Let me just have a look and see if there's anything in the chat here. So, yes, Oscar Escobar says, is there any criteria to define when a pump should have vibration monitoring? Does it depend on power or application? The bigger the pump, the more expensive it is, the more money you're spending on it. But most critically, I think, is it in critical service or general purpose service? How important is it to, if it were to break down? Prasenjit Khan says, I'm interested about vibration graph and vibration limit of API and 9906 standard. The vibration limit on API is, as I showed in the slides, it's 3 millimeters per second RMS. It doesn't include a vibration graph in that. The vibration graphs really, this is more detail than is the case within this short course. You need to review a more detailed course than this 40,000 foot course. Well, that appears to be all the Q&A. Let me just check again. Yep, that appears to be it. So it just leaves it for me then to say thank you for attending again today. I enjoyed presenting and preparing for this one. I hope you found it useful. See you all on the 18th of November, which is in 2 weeks' time, for the next short course. Bye-bye.